This is the video for section 11.9 on representations of functions as power series. And the point of this section is the following. So in the previous section we talked about when you have a power series, how to find its domain, that is the interval of convergence and the radius of convergence. And here what we're interested in doing is we're looking to see actually what functions we can get from this technique instead of just understanding the domains of those functions. And the basic starting point for this section is the geometric series. Which we'll write as the summation n equals 0 to infinity of x to the n, right? So this is our geometric series. And if you remember the notation that we had from geometric series, the initial term was a is going to be 1 in this case. That's when n equals 0, so we have x to the 0. And the common ratio of the terms in the series is r equals x, the variable that we're using here. And if you remember, the formula that we had for the sum of the series was given by a fraction 1 over 1 minus x. This is because a equals 1 and r equals x. And this is a valid formula whenever the absolute value of x is less than 1. In other words, the interval of convergence is the open interval from -1 to 1, and the radius of convergence is r equals 1. Okay? And what we're going to do is we're going to use this formula in order to build more functions out of power series. And here's the basic idea, is that if we change the variable, right, the variable is just a symbol where we can substitute some values in, so this formula can be rewritten as the summation n equals 0 to infinity of box to the n, where box is just a box to put things in. In particular, we'll put numbers in there, and the formula says that this is equal to 1 over 1 minus box for absolute value of box less than 1. Okay? So for instance, we can use this to find a power series representation for the function 1 over 1 minus 2x squared. So that's us using 2x squared in the box in this expression. And so the equality there says that I can put 2x squared in the box in the left-hand expression. So I rewrite this as the summation n equals 1 to 0 to infinity of the quantity 2x squared to the n. And we can do a little bit of algebra in order to simplify this. This is the summation n equals 0 to infinity of 2 to the n x to the 2n. That's multiplying out the exponent there. And if you like, we can write out a few terms of that. So when n equals 0, we just get 1. When n equals 1, we get 2x squared, and then we get 4x to the 4th, 8x to the 6th, and so on. And we know from the previous example that this is valid for, right, whenever our boxed expression is less than 1, so this is valid for absolute value of 2x squared less than 1. Dividing both sides by 2, that's the same thing as saying that the absolute value of x squared is less than 1/2. And taking the square root of both sides, that says the absolute value of x is less than the square root of 1/2. In other words, the absolute value of x is less than root 2 over 2. So it says that our interval of convergence is from negative root 2 over 2 to positive root 2 over 2, and our radius of convergence is root 2 over 2. Now, power series representations for functions, here's a big idea with this, is that what we're really doing is we're thinking of these things as infinite polynomials. And I put this in quotes because it's not a formal thing, this is just a way for us to think about it. So let's, on the next page, use this formula that we've just derived in order to compute a few more power series representations. Right, so here at the top of the page I've just rewritten the formula that we had from the previous page. With the range of x values that are allowed. That's the square root of 2 over 2 there. And now what we're going to do is we're going to use this metaphor for the infinite polynomials to get a power series expansion, say, for the function x over 1 minus 2x squared. And all I'm going to do there is I'm going to think of that as x times 1 over 1 minus 2x squared, perfectly valid algebra. And now I multiply x times the summation that we derived previously. And now thinking of this as an infinite polynomial, I can multiply the x through, and I end up with the summation n equals 0 to infinity, 2 to the n, x to the 2n plus 1, because x times x to the 2n just increases the exponent by 1. And again, we can write out a few terms of this. This is x plus 2x cubed plus 4x to the 5th plus 8x to the 7, and so on, which is the same thing that we would have gotten if we had just multiplied this expression term by term by x. Now, polynomials can be integrated and differentiated term by term, and we can do the same thing with these power series functions. Okay? One thing to keep track of as we do this is the radius of convergence. And so what we're going to do is we're going to integrate this function that we've just found the power series expansion for. So we're going to integrate term by term. And so we find, for instance, that the antiderivative of x over 1 minus 2x squared dx is the same thing as the integral of the power series that we found. Which, when I say integrate term by term, it means that I rewrite this as the summation n equals 0 to infinity of 2 to the n times the antiderivative of x to the n plus 1 dx. And this simplifies to the summation n equals 0 to infinity of 2 to the n times 1 over n plus 2 x to the, sorry, I rewrote that incorrectly. Let's fix that. So this exponent should be 2n plus 1. And so the new exponent I'll get here is 2n plus 2. And then there's a big plus c that goes along with that we'll take care of in just a second. Now, a particular antiderivative for this function you can get by doing a u substitution. So u equals 1 minus 2x squared, du equals minus 4x dx. And when you do that substitution and calculate the antiderivative, you find that a specific antiderivative here is minus 1/4 ln absolute value of 1 minus 2x squared. And what this formula says is that we can rewrite this as c plus the summation n equals 0 to infinity 2 to the n times 1 over, let's write that as 2 times n plus 1 x to the 2n plus 2. Right? And there's no c on the left, so we can find a c value that makes this true. And that's by plugging in x equals 0. So on the left-hand side we get negative 1/4 ln of the absolute value of 1 is equal to c plus the summation n equals 0 to infinity 2 to the n times 1 over 2 times n plus 1 x to the 2n. Sorry, we've plugged in x equals 0, so that's 0 raised to the 2n plus 2. And because n is ranging from 0 to infinity, I always have a factor of 0 on that side, so the entire right-hand side, except for the c, is equal to 0. The left-hand side is also equal to 0 because the ln of 1 is 0, so we find that c equals 0, and so we can rewrite this by saying that negative 1/4 ln absolute value of 1 minus 2x squared is equal to the summation n equals 0 to infinity 2 to the n times 1 over 2 times n plus 1 x to the 2n plus 2. One can, if you like, you can cancel off that one of the factors of 2 inside this expression with the 2 in the denominator to simplify a little bit. I'm not going to worry about that for this lecture. Last thing to note here is, again, the radius of convergence stays the same. And so we pretty much know exactly where this power series converges. Inside the text, for instance, in Theorem 2, let me just write a little note over here. So Theorem 2 talks about some rules for differentiating in the general case, where our power series is not centered at 0, but is centered at some number a, right? So we have something of the form summation over n, cn, x minus a, quantity to the n, and that talks about the integration and differentiation patterns that we see for that. And if you like, inside the textbook, there are a number of examples of computations like this that you should look at before we meet in class. And of course I will do at least one example like this in class before we start working in groups. So this is the end of the lecture on section 11.9.